Hi everybody. Today what we're going to do is we're going to look at this Riemann sum and then try to rewrite it as a definite integral. Alright, let's have a look. So I've shrunken down the problem, so now we can see. So obviously at first glance it doesn't really look like this can be written as a definite integral unless you know how to do this already. Let's look at what this sum represents. So basically, this sum is looking to find the area under this curve. The area under this curve. If we break down the stuff under the curve into equal rectangles, and then there are certain. So as we look at this, with our limit here, n will be the number of subintervals. So it's taking the limit as the number of subintervals if you break this down as approaches infinity. So these get like skinnier and skinnier. And one thing to note is that they're all subintervals of equal length or width. Sorry. So let's keep looking at this. So what we're going to do is we're going to look at a generic form of this before we tackle the full question. All right, so the Riemann sum is basically an introductory way to examine the area under the curve of a function. So how this is found is obviously we have that limit, and it's the sum of all the little rectangles underneath the curve. No, it's not a really little rectangle. Sorry. So it's the sum of the area of the rectangle. So this will be the sum. What's inside the sum is what's being added up. So this will be the area of the rectangle. So as we remember, the area of a rectangle is length times width, okay? Or not okay, but like that's something you probably remember from a while ago. So the area of a rectangle is going to be length times width. So that applies to here. So if this is our area, we have the height of the rectangle is going to be the f evaluated at the ith subinterval, and the width there. So the width of every subinterval is the same, so it's just delta x with no I. So obviously I goes up with everything. So let's say we have a curve. So we're going to try to find the area under the curve. So let's say this is x0. Oops. X0 is there, x1 is there, x2. So that's like the terms, right? So that is xi, and then just I is 0 here, I is 1 here, I is 2 here. So let's say I'm trying to find the height at x2. It would be the value of the function. Let's say this thing is f of x. It would be the value of function at x2 would be here, and then the width of that rectangle would be delta x. So there are multiple types of Riemann sums, but for now we're just looking at converting it into a definite integral. So we're going to look at some definitions here. So let's say we're only trying to find the area under the curve between 2 points. So let's say our starting point is A and our ending point is B. So, and let's say the number of rectangles we're using is going to be n. So n equals the number of rectangles we're using. If I draw it, I can't draw. Okay. So number of rectangles. Okay. So to find the width of every rectangle, when all rectangles are of the same width, we're going to have to take this length and then divide it by the number of rectangles. So this length can be found by b minus a, And then to get the width of each little rectangle here, we have to divide it by the number of rectangles. So that's how the width of each subinterval can be found by b minus a over the number of rectangles. Okay, so all right, to find the let's say we're trying to find what x2 is, like which x value is x2. So x2 is a number of rectangles away from A. So let's say your starting point is A. Then we add on how many, like which, so let's say this is 2. Wait, so x2 is equal to A plus 2 times the width of the rectangle. That makes sense because there's been 2 rectangles before x2. And then this width here is going to be where x2 is. So it'll be the lower bound plus which rectangle it is times the width of the rectangle. All right. So if this doesn't make that much sense, we're just going to apply these two. And actually this, we're going to apply all 3 of them towards our example at the beginning. So the hope is that you understand, but even if you don't, you're just going to look for these 3 things in the question you're given. So we're going to look for something that looks like this. All right, so what you see on the screen now is our original question, but I've written the generic form of this right beside it. So even if you don't understand it completely, it is a very good idea to know what this is, to know to look for something that looks like this. So now we're going to look for things inside of this that look like the things in this. So okay, so the 2 extra little formulas I wrote down, or like relationships I wrote down, are going to help us with this. So if we remember that the width of every little rectangle is going to be the upper bound minus the lower bound all over the number of rectangles. And then the position of our ith rectangle is going to be the lower bound plus the number of rectangles before it times the width of every single rectangle. So we're going to look for something over n in our original to be, so in our generic form we have a delta x. Delta x is a b minus a over n. We're going to look for something in our question that looks like, something in here that looks like a b minus a over n. So if we, so it helps that I've written it in the same order here, but we can know that the 2 minus n will be our delta x term. So what we can do here, we can set, so our delta x in our problem is going to equal to 2 over n. And then this is also equal to the thing that's true for all of these, which is the upper bound minus the lower bound over n. So now you have a choice to make. So now we can pick any numbers for a and b such that the difference between when you subtract b and a, like when you subtract a from b, you get 2. So you can pick any number in the world. You can pick 6, 7, you can do whatever. But the easy thing here to do is this, we're gonna let b equals 2 and a equals 0, which is a valid choice because b minus a is equal to 2. So we're going to keep these values as this will be important for our definite integral. Okay, so now that we've established what delta x is, the rest of the stuff inside our our summation here will be the function of xi. So this means that the function of xi, f of xi, will be equal to the ln, or the natural logarithm, of 1 plus 4i over n. But we want to write this as a definite integral that doesn't depend on I, because I is the thing that only exists for our sum here. That's our like dummy variable for our sum. So we're given the function of xi. We can also, but first, I think it might be useful for us to find what xi is. So we also know our xi. So the position of our ith subinterval is equal to the lower bound plus the number of sub-rectangles before. Oh, the position of the ith rectangle is equal to the what do you call it? The lower bound plus the number of rectangles before it times the width of all the rectangles. Sorry. So we can look at this here because now we have an a value and we have our delta x value, or like our expression. So now we can find xi. So it's our lower bound plus the number of rectangles before times the width of the rectangle. So we have a equals 0, or lower bound is 0, plus I. I is a dummy variable that goes up by 1 each term in our series. That is denoted by our sigma sign here. And then delta x is 2 over n. Oh, shoot, sorry. Is 2 over n. If I write this out properly, this is 2 I over n. All right, so now that we have our xi expression, we're gonna look back into our function of xi to look for something that looks like our xi expression. So in some cases, there will be a direct match. So the value you find here will actually appear up here. But we notice that something's a little bit different here. You can kind of see you have a 2i over n here and a 4i over n here. I can factor, or I don't even know at this point. I can rewrite this as the ln of 1 plus 2 times 2i over n. So what this gives me, the f, or oops. Sorry. So the function of xi is equal to the natural log, or ln, of 1 plus 2xi. All right. So let's look at the form of our definite integral. So the definite integral has no plus c because it's like a number. It's like the actual sum evaluated. So the most accurate form of that. So the integral from the lower bound a to the upper bound b of a function with respect to x. So notice in our original we had a delta x and a dx. So remember when we did differentials is like a really tiny change in x. This one is just the change in x. However, this went smaller and smaller as the number of rectangles. This is the width of the rectangle, remember? And as the number of rectangles went to infinity, our rectangles went skinnier and skinnier. So this is like the skinniest possible rectangle. So what I can do now is I can write this, sorry, change my pen back. So now I can write this sum knowing our f of xi function and our delta x value, our width of a rectangle, knowing that, we can rewrite this in the form of a definite integral. So what that gives us, so we have our integral from a to b, but we did solve for a and b at the start. So our a value, our a value is going to be 0, and our upper bound will be 2. And then our f of x is just going to be the same over f of xi in terms of xi, with just like subbing this out to get our xi. So we just replace xi with an x. So everywhere we see an xi, we'll make an x. So we have the natural log of 1 plus 2x, and then our delta x, our delta x here turns into a really very small delta x, so that just carries over. All right, so that is basically it. However, let's say you have a multiple choice exam and you want to look for multiple possible answers. So the reality is there are infinitely many possible answers here. So because since this evaluates to just the number, so if I had every single one of these, this would evaluate to a number, because we're taking it from, okay, I kind of forgot why, but it will evaluate to a number. But there are some changes we can make to this form such that it still maintains this, it still equals the same number. So we can manipulate our upper and lower bounds and it's something inside our function. So let's have another look at that. All right, so what you see on the screen, we have our answer, one possible answer to our problem, and we're going to try to find another possible form of the answer to our problem. So, so what we can do is we can change the bounds of our integral. So we're modifying our upper bound to go from 2 to 67. So actually, okay, scratch that. We'll make the lower bound 67. So remember when we did this, when we found this form, we found that the upper bound minus the lower bound had to be 2. So we can pick any numbers for a and b such that their difference is 2. So we did 2 and 0 our first time. So the difference between my lower bound and my upper bound has to be 2, no matter what they are. So if my lower number is, okay, so if we started with an upper bound of 0, or of 2, sorry, and a lower bound of 0, and that gave me 2. So now, let's go, instead of question mark, let's go, this won't be scribble. Okay, so to keep question mark and scribble different. So we had, so now our upper bound minus our lower bound still has to equal 2. So our upper bound is unknown, and I wrote it as question mark. I already changed it. I'm probably not going to change it again. And our lower bound is now 67 and 2. So question mark, if we isolate, will be 69. So this is still a valid upper and lower bound for this integral, because obviously the difference between them is 2. However, if I have 69 up here and I have the exact same stuff inside, this will not be equal, because you are evaluating the function at the bottom number and all the way up until the top number and taking the area under the area under that curve region. But this is a different area, so we have to adjust inside our function. So we have to compensate for that. So notice how we added 67 to the upper and lower bounds. So inside our function, 1 plus 2x, we would have to, let's make this a different color. I can't find a different color. That's not good. We would have to subtract that same that same number from inside our function. So at every point of our function will be that much less because we are this much more where we're evaluating it. So in the end, this will be equal to the definite integral from 69 of the natural ln of this. So it'll be 2x minus 66, right? Because 1 minus 67 is this. Okay, so that will hold true. So let's go ahead and generalize this so that you can apply it and see. And then if you don't see your original answer as one of the multiple choice options, you can find a look for a number. You can look for a different one that still might be correct, given if you, obviously you would have to calculate this correctly first. So generically, I don't think I need more room for this. Let's see, knock on wood. So if I have the definite integral from a to b of f of x with respect to x, this is also equal to the definite integral from a to b, actually the integral from a plus anything to, so it's the definite integral from a plus anything to b plus anything, the same anything, so that's why they're both smiley faces. However, inside my function, you would have to subtract the same anything for this to be equivalent. All right, so this is also applicable to the original sums in the question, but this might be useful if you're asked to rewrite a Riemann sum as a definite integral, and the answer you found is not the one available to choose as one of your A, B, C, or D, or E. So what we can also do is, if we had our original form, the sum, actually we're not going to have the limit thing, so we're just going to have the sum from I equals 0, let's say I equals 0 to 2 of f of x. It's going to also equal, so let's say the sum from I equals 0 plus smiley face to 2 plus smiley face, and then each element in our sum would also have to have this subtracted from each term. Now if we look at that, so now with our sums, it's actually a little bit easier to look at why this is true. So let's have a look. All right, so let's go through a quick reason why this is true. So we're gonna try to prove this is true. So let's look at our right side by itself for now. So we're gonna start with our 0th term, and in our 0th term, the inside function being summed is I plus 1, so it'll be 0 plus 1, so it'll be 1. In our first term, because we started at 0, I plus 1 will be equal to 2, because well, I will be equal to 1, and then this will be 1 plus 1. And this one, in our second term, when I equals 2, that's our ending term. we will have let's say oh yeah, 2 plus 1, which is 3. So if I looked at this would be the 0th term plus 1 plus this will be the first, oops, so notice, even though we had 0 all the way to 2, we had 0, 1, and 2, each of our terms had a plus 1 on it, so it would be the same as what our result would be here. So if I had the sum of I from I equals 1 to ending at 3, I equals 1 is our first one, so obviously this is that. So notice how these are the same. This is a little bit too simple of an example for this, but notice how when we adjust our starting and our ending I values, we had to adjust inside our sum and add plus 1 to each of them for this to be true, for these two to be equal. I'm missing the left side there. So hopefully that, even though it was a stupidly simple example, that like showed you why, like, even though we started at 1 and ended at 3 here, this time we started at 0 as I and then ended at 2 as I, we add an offset there. So actually, let's go. So I could also write this as the sum of from I equals 5 to 7 of I. So since I added 4 to each the top and the bottom, if we like started with this, I would have to subtract 4 in each term. So let's go. Okay, the upside, I don't know. So this thing will be equal to 5 minus 4 plus 6 minus 4 plus 7 minus 4. So notice, even though I started at 5 and ended at 7, the minus 4 makes this still equal the same. So 1 plus 2 plus 3. So hopefully this example helps illustrate this better. So what I can see is that if I add, if we started I equals A and end at B of a function being summed, or something being summed, this would be still equal. So if I started at A and I add a number, my ending number would also have that number added to it. However, our inside would also have this subtracted from this. And obviously, since I was just from 1 to 3, this was an easiest way to write this sum. I would take this time to remind you that that there are some formulas that you can remember for this, so you don't have to expand it out and then evaluate it. So here it would be the upper limit times the upper limit plus 1 all over 2. So here this would be, the upper limit is 3, the upper limit plus 1 is 4 over 2, and then this is, those will cancel obviously, but then this will be 12 over 2 to give us 6. All these are also equal to 6. So, however, this identity only works for, it should only work for sums that are from I equals 1 to a number. So this is why we're not just getting it from I equals 1 to get here. We're more likely going to use this identity or this process here so that we can use our properties of sums that start at 1 and go to n. So there's the sum of 1, the sum of I, and the sum of I squared. So I would review this if I were you next. All right. I tacked on a little bit more extra connected knowledge at the end, but I hope that helps you in your practice. Have a great day, and good luck with your work.